So in the last lecture, we defined topology on the product space. So we have already seen this. Already seen the product topology on the Cartesian product x cross y, where x and y are two topological spaces. Okay. So now today what we do, we now generalize this definition to more general Cartesian products. So this means what we are going to do, we are considering the following Cartesian products. We consider the following Cartesian products. So what are they? Number one, a finite and topological spaces, say x1, x2 to xn. Then let us take this Cartesian. And second one is an arbitrary Cartesian product where we do not know. So here this is a countable Cartesian product. Okay, and there will be an arbitrary countable, an arbitrary Cartesian. Okay. Correct. I think there is some problem. Wait a minute. Okay. So there are so we will consider these. So number one, finite Cartesian product, and second one is an arbitrary Cartesian. Okay. So there are two possible ways to proceed. So possible ways to proceed. So one is, the first one is take the collection. So in similar fashion that we did in case of two topological spaces. Here we have n to n and so here we have n topological spaces, and in second case we have an arbitrary collection of topological spaces. Okay, so what we do, we make a base. Okay, so this collection u1 cross u2 cross un, where ui is open in xi. and this is true for all. Okay, take this collection. So B1 is the collection of all sets of this form U1 cross U2 cross so on cross UN, where these UIs are open subsets of I, and this is true for all I, right? So this collection is the base. Take this collection is a base for the topology on X1 cross X2 cross X. Okay, this is one way, and similarly, so this is for the first collection. So this Cartesian product. We have another Cartesian product, which is our collection of Cartesian product of arbitrary number of topological space. In this case, take the collection of say of all sets of this form, okay, where this UI these are open sets in Xi. This is true. Okay, and take this as a base for topology on X1 cross X2 cross and so on. Okay, we call this the box topology. Okay, good. Second way, so this is the same thing we did for the product topology for X cross Y. Remember that. Okay, this is the same thing that we did here. Here is the second way. Now, second way is we will define topology via first we will define subbase. Okay, so if you remember, how did we define subbase? We first take projection maps. Okay? We first take projection maps, and then we define a subbase. So which was the collection of inverse images of open sets under projections. Okay, so we did the same thing here. Second way, we do the same thing here. Right? Okay, we take as a subbase all sets of the form pi I inverse ui. You know this pi I in, so we did the same thing in case of the product topology on X cross Y. Remember, okay? Where here this I is any inductions. I is okay. So this is some index. And UI is an open set of X. Okay. Then the collection S, which is pi I inverse UI, where UI is open in Xi for all I in some indexing set. Okay. So we take this collection as a subbase, and we will call this topology the product topology. Okay, this we will call the product. Okay. So in case of you have already seen that when we have only two topological spaces, these two topologies are same. See, we define the product topology via this definition, and then we via this definition for so I'm talking here about the case X cross Y, the Cartesian product of two topological spaces. Okay, so we define like this, and then we showed that the, this collection will be a subbase. Okay, so in the case where we are considering the Cartesian product of two topological spaces, the box topology and the product topology are the same. Okay. So in fact, so here is the remark. In fact, uh, these two topologies agree for the finite Cartesian product. Okay, Cartesian product, and differ for the infinite product. Okay, why we are saying this? We will see why we are saying this thing differ for the infinite product. Okay, we will see this. So for this, what we do, we will consider the base element. We will consider a generic base element. Okay, let us consider a base element B for the product topology, means for the second topology. Okay, product topology. So the product topology means this one, which is generated by this subbase S. Okay, for the product topology on this Cartesian product, so infinite Cartesian. Okay, so since this B is a base element, and we know from a subbase how do we get base elements? Base elements are finite intersection of members of subbase. Okay, so then B is a finite intersection, okay, of members of subbase. Okay, that is, so what are the members of subbase? These are this collection phi I inverse ui. Okay, and we are taking only finite number of this set. So say for I equal to I1, I2 to Ik. Okay, so these are fine. So this B is this collection intersection, say n equal to 1 to k phi in inverse uin, okay, where uin is an open set of in for all in I, and this n is okay. So this collection is, so this means any base element will be of this form, will be of this form. Okay. And here uh, we have not imposed any conditions for other I. Other I means other than I1, I2, Ik. Okay. So, so then any point x in B, okay, any point x in B, uh, so any point will belongs to B if and only if any point x belongs to B, or so let me say like this. Then x belongs to B if and only if pi I x belongs to Ui for I equal to I1, I2 to Ik. Okay, and there is no restriction on pi I x for other values. Okay. Correct. So this is the product. So a base element for the product topology in an infinite Cartesian product. So before proceeding ahead, so we all know finite Cartesian products, okay? But let us define the Cartesian product for an index family where this indexing set is arbitrary, any arbitrary, completely arbitrary. Okay. So first define the Cartesian. So here is the definition. So we are now defining the Cartesian product of an index family of sets, okay, where the index set is completely arbitrary. Let J be an index set. Okay, this be an index set. So given a set X, given a set X, we define J tuple. Like n tuple, we define now J tuple, okay, of elements of X to be a function. Function, say X from J to X. Okay. How do we define? Like this. We define like this. If alpha is an element of J, if alpha belongs to J, we denote the value of X at alpha by x alpha. So you know we always write x of alpha like this. So we denote the value of x at alpha by x alpha rather than x of alpha. We will not write this, but we will write x. Okay. We call this x alpha, we call it the alpha coordinate. X. Okay. And we denote the function and we denote the function x self by this symbol. Find it. So this is shorthand for the J tuple. Okay. By this symbol, which is as close as we can come to a tuple notation. So this is a tuple notation. Okay. Tuple notation for an arbitrary set. Correct? So here we have, so here what we did, we have a set x, okay? We have a set x, and suppose j equal to 1 to n, okay? Then uh, then then an n tuple. So here or so the j tuple in this case is nothing but the n tuple. J tuple in this case is an n tuple, okay? And this is a function now. So n tuple is a function x from j to x, okay? And x of j is, we are writing xj, okay? J belongs to j, okay? So all the, so this, we will write this as x1, x2, xn. And these are called, this is first coordinate, this is second coordinate, this is nth coordinate. So we have generalized this n tuple notation to an arbitrary index set. Okay, so to j tuple. Correct? Did you? I think you are getting this thing. If you face any problem to understand these things, you may ask. Okay, anytime. Okay, next thing, next definition. So here we will take an index family of sets and we will define its Cartesian. Okay. So let A alpha, where alpha comes from the the index set J, be an index family, okay, of sets. Let x equal to union of A alpha. X is the union. The Cartesian product of this index family is denoted by this product alpha, where is J A alpha. Okay, and is defined to be the set of all J tuple. Now you know what a J tuple is. X alpha, alpha in J of elements of X such that X alpha belongs to A alpha for all alpha in A. That is, it is the set of all functions. Okay? So this is the set of all functions from J to X. Here X is union of A alpha such that X alpha, which we are writing X alpha belongs to alpha for all alpha in J. Okay. So this is easy thing. This one is easy thing. So so this is just for your so to sharpen your memory. You all know these things. Okay. Now we define box topology on this Cartesian. So on this Cartesian. Okay. So definition. Let alpha belongs to J, where J is an index set, be an indexed family of topological spaces. Okay. Let us take as a base for a topology the product space on the product on the Cartesian product. Call on the Cartesian product by alpha in J. And what we are taking, so let us take as a base this collection, the collection of all sets of the form, you know which form, of the form pi alpha in J U alpha, correct? Okay, where these U alpha, these are open sets. Okay, where open in X alpha for all alpha in J. The topology generated by this base is called the box topology. Box topology. Okay. So this is the box topology. So you can in fact check that this collection U alpha is open in X, open in X alpha for all alpha in J is in fact a base. Okay. So how do you do this? So so it is easy. Okay. For any X alpha in J, any tuple, okay, any J tuple in this Cartesian product, for any such thing, okay, any element of this Cartesian product, okay, you may choose B equal to this as the basement, but because each X alpha is open in Excel, okay, you may choose B as this and such that X alpha in J belongs to B, which is nothing. So to show this is the base, first thing is this, and second thing is the take intersection of two base members. Okay, take, suppose we have two base members. Suppose B1 is pi 1 alpha in J U alpha and B2 is pi alpha in J P alpha. Okay, then what you do, you take B1 intersection B2, and your claim is their intersection is itself their intersection is you will show this is the base. Okay, for J V alpha. Okay, so but this is nothing but so product of alpha in J U alpha intersection V alpha. You see this U alpha is an open set in X alpha, V alpha is an open set in X alpha, U alpha comma V alpha are open in X alpha. This implies their intersection U alpha intersection, finite intersection of two open, so finite intersection of open set is open in any topological set. Okay, is open X alpha. Therefore, B1 intersection B2 belongs to this collection of bases. Okay, so here this means this collection B, which is here, this collection is a base for a topology on this Cartesian product of index family, and this topology is called the box. Okay, so now we have also seen the sub-base formulation. Now let us generalize that sub-base formulation. Okay, now we generalize the sub-base formulation of the definition. Okay, so you know, please remember, while talking about sub-base, we first we considered the projection, okay? The projection. Let phi beta, which is a map from this Cartesian product to x beta, okay, be the function assigning to each element of the product space of this, okay, it's bth coordinate, it's the beta coordinate. This means phi beta of x alpha in J is nothing but x. Okay, it is called the projection mapping associated with the index beta, called the projection mapping associated with the index theta. Okay. Now using this projection, we define uh, the product topology, which is the topology generated by the subbase. So definition. Let S beta denote this collection. S beta denote the following. Okay. So you all know S beta would be inverse image of U beta under pi beta. Okay. U beta is open in X beta. So take this collection S beta and let S be the set of all unions of S beta. Okay. Means union of this collection. So and S is union of S beta beta in J. Okay, take all such collections. Okay. The topology generated by S, topology generated by S is called the product topology. Okay. And in this case, this topological this topology space called the product space, the product space. Okay. So we have already seen that product space and the product space means the product topology or finite Cartesian product is same as the box topology in the finite Cartesian product. So this is what we will. Next, we will see we will compare the box topology and product topology for infinite infinite Cartesian. Okay, so we will do this in next lecture. Okay, I'll stop here. We will do this in next lecture. Comparison. So what we will do is comparison between box topology and product topology. Okay, so we will do this in next. So I'll end this meeting here. Okay.